My presentation is on the differentiation of embryonic stem cells to create insulin-producing beta cells for the treatment of diabetes. This presentation is based on the paper Direct Differentiation of Embryonic Stem Cells Towards Insulin-Producing Pancreatic Cells by Ipsita, Banerjee, and Martin Yarmush. The paper described an attempt to direct cell differentiation by mimicking the natural development of the human pancreas. First, the scientists initiated the pancreatic development pathway by placing the cells on a thin layer of matrigel and used retinoic acid to enhance the expression of the PDX1 gene. Activation of this gene expressed the gene NGN3, which initiated a cascade of transcription factors that caused the cell to differentiate into one resembling the endocrine cells of the pancreas. Banerjee and Yarmush then co-cultured the mature pancreatic cells with endothelial cells to create the strong insulin expression that is characteristic of beta cells. Type 1 diabetes is an autoimmune disorder that destroys the beta cells of the pancreas. These beta cells produce insulin, which is a hormone that is essential to maintaining glucose homeostasis in the human body. When the beta cells are destroyed, the low insulin levels cause hyperglycemia, an abnormally high blood glucose level. This causes numerous complications, including heart disease, kidney disease, and blindness for the millions of diabetics in the United States. The autoimmune reaction that causes diabetes only destroys one type of cell, the beta cell. Because of this, the disease lends itself to cell replacement therapies. Other than human donors, the best source of replacement beta cells is the differentiation of embryonic stem cells. Embryonic stem cells are useful for cell replacement because they can renew themselves indefinitely, providing an unending supply of starting material. They are also pluripotent, so they can generate any type of cell in the body, from neurons to skin cells. The stem cells can be directed to differentiating into a certain type of cell through chemical treatment. To effectively treat diabetes patients, the replacement beta cells developed from stem cells must be able to produce, store, and release insulin in adequate amounts. They must also respond quickly to changes in glucose level and to potassium chloride stimulation, because too much insulin is even more dangerous than too little. The propagation of the cells must also be limited to prevent a beta cell mass from accumulating in the body and causing hypoglycemia. Scientists understand two methods of beta cell differentiation. The first is spontaneous, where embryonic stem cells are simply allowed to aggregate. This condition mimics gastrulation, which is an early phase of the development of all animal embryos. However, only 1 to 3% of cells differentiated in this manner express insulin at all, and none of these insulin-producing cells are physiologically normal. Though these cells have been shown to restore normal glucose levels in diabetic mice, they cannot be an effective treatment for humans. A more effective method for differentiating functioning beta cells is one that attempts to closely follow the normal development of the human pancreas, with specific chemical factors added to initiate and promote beta cell growth. One engineered protocol for differentiating beta cells begins by inhibiting p13 kinase and treating cells with high amounts of activin A, a protein that regulates endoderm development and pancreas specification. Cells that then display the SOX17 and GATA4 markers of endoderm development are brought further through the pancreatic path with the introduction of cyclopamine, the production encouraging FGF10, and the removal of activin A. This promotes the appearance of HNF1 beta and HNF4 alpha transcription factors that elevate the transcription of the insulin gene and PDX1, which is essential for pancreatic development. Finally, retinoic acid is added to signal the patterning of the cells towards pancreatic development, and IGF-1 and human growth factor are added to sustain beta cell proliferation. This process results in a 12% yield of insulin-producing cells. However, most of these cells produce insulin and glucagon, another pancreatic hormone that opposes the effects of insulin. This indicates that these cells are not identical to natural beta cells, which exclusively produce insulin. This inefficiency makes it difficult for these cells to reverse the hyperglycemia caused by diabetes, and they are not a viable treatment for humans. GLP-1, a protein similar to glucagon, has been added to the later stages of this process in an attempt to improve the insulin yield. GLP-1 can enhance insulin secretion and promote differentiation, but not enough to yield cells able to treat humans. Another improved process has been engineered, mainly for mouse embryonic stem cells, with several small differences from the previous procedure. After treatment with activin A, the differentiated cells are cultured with insulin transferrin selenium solution, ITS. Then, after retinoic acid treatment, the cells are treated with a combination of ITS, basic fibroblast growth factor, and epidermal growth factor for 3 days. The cells are then again treated with fibroblast growth factor and nicotinamide for beta cell maturation. Cells developed by this process express the beta cell specific genes insulin 1, insulin 2, PDX1, and other endocrinal markers. Though these cells exclusively produce insulin, it is still at lower levels than natural beta cells. The cells respond normally to both glucose and potassium chloride stimulation and are the closest embryonic stem cell derivatives to natural beta cells. However, these still aren't good enough to treat humans. Because the yield of insulin-producing cells and the insulin levels of stem cell-derived beta cells remain very low, chemical engineers have a lot of room for improvement. New methods are being developed to better purify the beta cell from the group of differentiated cells for transplantation. Processes are also being developed that even more closely resemble natural cell differentiation, with the possible addition of hepatocyte growth factor and follistatin, a protein that promotes proliferation and cell differentiation. Engineers are also trying to find ways to speed the process and make it less expensive so that the potential treatment could be more readily available. It is obvious that improvements are needed before engineered beta cells can be used to treat humans, but the progress chemical engineers are making in the development of replacement cells may one day create a cure for type 1 diabetes. These are the sources I used in creating my presentation.